Okay, so welcome to mathematics class, and now we are going to talk about quadrilaterals. So let us see what are the topics to be covered. So first we will have a brief introduction, then we will learn about the angle sum property of a quadrilateral, then we will talk about types of quadrilateral, then we will talk about parallelogram, then we will learn about another condition for a quadrilateral to be a parallelogram. Then finally we will look at the midpoint theorem. So let us start off with the introduction. So we all know that quadrilaterals are closed figures which have 4 sides, 4 vertices and 4 angles, right? And here you can see a figure. I think you know what is it. It is rectangle, right? And here you can see 4 vertices are named as A, B, C and D. So how do we name these figures? These 4-sided figures can be named either in the clockwise direction or in the anti-clockwise direction. Like here, the first example, we can name it as quadrilateral ABCD, which you can see is in anti-clockwise manner, ABCD, or we can name it in clockwise manner also, DCBA. And you can see we can start off with any vertex, right? For suppose for clockwise we start at A, so our name would be ADCB, right? So this is how we can name any quadrilateral. Just remember to follow the name in a cyclic order, either anti-clockwise or clockwise, and write the names of the vertices one after the other as they come accordingly. So let us move forward. So let us learn about what are diagonals. I think you know what they are, right? And you can see diagonals are those lines which joins the opposite vertices. Like here you can see 2 opposite vertices, the opposite vertices like A and C here are joined, like, and you can see B and D are also the opposite vertices. So you can see we have joined the 2 opposite vertices, and these lines, the white lines which are shown here, the lines joining the opposite vertices can be called as diagonals, and diagonals can be named in the same way we name line segments like AC and BD, right? So these are the line segments or diagonals, right? The line segments which join the opposite vertices of a quadrilateral. And also you can tell 2 non-adjacent vertices are joined with a diagonal, right? You can see A and C are non-adjacent while A and D are adjacent vertices. So the line joining 2 non-adjacent vertices are called diagonals. So let us learn about 2 classes of quadrilaterals. The 2 classes are convex and concave. You can see the first type is called convex, and why is this? Because you can see all the internal angles are acute angles, right? All the internal angles are acute angles or obtuse angles. This angle looks like an obtuse angle, this angle looks like an acute angle, and so on. You can just figure out which angles are what, and you can see that none of the angles cross 180 degree, right? So such quadrilaterals are called as convex quadrilaterals. Now what are concave quadrilaterals? You can see the vertex D. At vertex D, what is the angle at this vertex? Angle ADC, the angle which is made at the internal side of the quadrilateral. I think you can see that this angle looks like a reflex angle, right? It is more than 180 degrees. So such quadrilaterals having one angle more than 180 degrees or one of the angles as a reflex angle, such quadrilaterals can be termed as concave quadrilaterals. And you can see it is concave outwards, right? You can see it is concave outwards, or in the first case it was convex outwards, right? I think you know about what is concave and convex from light, right? We have learned in physics about light, and we have talked about mirrors, right? We have talked about different types of mirrors and lenses, and there we have learned about what is convex and what is concave. And here the same concept can be applied to what is concave and what is convex. So keep in mind, convex quadrilaterals are those which have none of the angles as a reflex angle, and concave are those which have one of the angles as a reflex angle. And obviously, if one of the angle is a reflex angle, the rest of the angles has to be acute angles. So let's come to our next topic, the angle sum property of a quadrilateral. Now this states that the sum of all the angles of a quadrilateral is always 360 degrees. And how is it so? Let us find out. Let us look at the convex and concave quadrilateral once again. So we have told that the sum of all the angles of a quadrilateral is 360 degrees, or angle A, angle B plus angle C plus angle D must give us 360 degrees, right? So let us see how. We divide the quadrilaterals along their diagonal. We divide the quadrilateral along their diagonal. You can see we have divided the first quadrilateral based on the diagonal AC and the second one according to the diagonal BD, right? And now I think you can see two triangles within them. This is one triangle and this is one triangle, right? And what is the sum of the angles of a triangle? These angles. What is the sum of angles of a triangle? It is 180 degrees, right? And for this triangle, it is also 180 degrees, right? And what are the angles of a quadrilateral? Angle B and angle D can act as the angle of quadrilateral itself, and angle A and angle C, you can see that the sum of the angles of these two triangles can give us angle A and angle C, right? So a quadrilateral consists of two triangles, right, when divided along their diagonals, and as the sum of the angles of one triangle is 180 degrees, when two triangles are joined back to back, their angle sum comes out to be 360 degrees. And what is the figure formed when two triangles are joined back to back? It is a quadrilateral. And for the concave one also, you can see we have this triangle ADB, and the second triangle we have is DCB. So the sum of the angles of the first triangle is 180 degrees, the second triangle is also 180 degrees. So when they are joined back to back along the side BD, we get the sum of the quadrilateral, the sum of the angles of the quadrilateral as 360 degrees. So just keep in mind what is the angle sum of all the angles of the quadrilateral, right? It will come in handy in solving questions. So let's talk about different types of quadrilaterals. The first type we talk about is a trapezium. So you can see what a trapezium looks like. Here ABCD is the trapezium we are talking about. And what are its special characteristics? Why is it termed different from all other quadrilaterals? You can see here the one pair of opposite sides are parallel. In this figure, side AB is parallel to CD, right? AB is parallel to DC here, right? I am naming according to the direction in which they are parallel, and you can also name in the opposite direction also, like AB parallel to CD also you can tell, it doesn't matter as long as they both are line segments. Okay, so you can see here the one pair of sides is parallel, but the other two sides here you can see AD and BC are not parallel, right? They can be equal in length, but they are not parallel to each other. So such figures with only one pair of parallel sides are called as trapezium, right? And if the other two sides become parallel to each other, that figure is called something else. We will look at it, but keep in mind what is a trapezium. Trapeziums are those figures which have only one pair of opposite sides parallel, or trapezium are those figures in which two opposite sides are parallel to each other. So let us talk about the new figure which we were thinking about, the parallelogram. In this figure, the opposite sides and all the opposite sides are parallel to each other. Both the pair of opposite sides AB is parallel to CD, and separately AD is parallel to BC. You can see both the lines are marked parallel, and they are given different colors to show that AD is not parallel to AB, right? No two adjacent sides are parallel to each other, and obviously they can't be parallel to each other, or how will they form a closed figure, right? If they are parallel to each other, that means either they are overlapping onto each other or they are not meeting at all. So you can see the red arrows are showing one set of parallel lines, and the blue arrows show another set. The blue arrows shows another set of parallel lines. So you can see AB is parallel to DC and AD is parallel to BC. Such figures with all the opposite sides parallel to each other are called parallelograms. So we have seen in trapezium only one pair of parallel sides, but in parallelogram we have seen both the pairs of opposite sides are parallel to each other, right? So let us look at a very common figure, the rectangle. So what is so special about it? Rectangle is actually a special case of a parallelogram, and here the opposite sides are parallel to each other, or AB is parallel to DC and AD is parallel to BC. But what is the special criteria for being a rectangle? All the angles must be 90 degrees, or all the sides must be perpendicular, all the adjacent sides must be perpendicular to each other. So rectangles are nothing but parallelograms with all angles equal to 90 degrees, right? So you can see here AB is parallel to DC and AD is parallel to BC. Also in rectangle, opposite sides are equal to each other, right? I think you know this characteristic, right, of rectangles. Opposite sides are equal, or here you can see with the red lines it is shown AB is parallel to DC, or AB is equal to DC also, and with blue lines it is shown AD is equal to BC, right? So in rectangle, opposite sides are parallel and equal to each other, and also the angles, all the angles measure 90 degrees, right? So what we have learned till now, we have learned about trapezium, the parallelogram, and a special case of parallelogram which is the rectangle. So let us look at the next figure. Next figure is the rhombus, and I think you can see here rhombus looks almost like a parallelogram, but it is somewhat special. Rhombus is also a special case of a parallelogram where all the sides are equal. You can see here all the sides are marked with the same line, with the same red line, to show that all the sides are equal. So as rhombus is a special case of a parallelogram, that means rhombus also must have all the characteristics of a parallelogram, like the opposite sides are parallel to each other, right? Here you can see AD is parallel to BC and BA is parallel to CD, right? So these are the two pairs of opposite sides which are parallel to each other, and also all the sides are equal. All the sides are equal to each other. AB equals BC equals CD equals DA. So this is what a rhombus is. So let us talk about square, the most common figure we use. So you can see here, here the square is named as ABDC. So we will have certain changes here, don't worry. So what is a square? Square is also a special case of rhombus, or you can say a special case of a parallelogram. Why it is told as special case of a rhombus? Because it has all the characteristics of a rhombus, where the opposite sides are parallel to each other, and also all the sides are equal to each other. So what is so special about squares? Squares have all the angles 90 degree, just like a rectangle. So almost like a rectangle, square has all the angles equals 90 degree, but all the sides are equal and the opposite sides are parallel to each other. So you can see here AC is parallel to BD, AB is parallel to CD, and all the sides are equal. AB equals BD equals DC equals CA. So let's talk about a new shape, which is a kite. I think you know what a kite is, right? And it almost looks like this, right? So what is so special about this kite? Kite can be any random shape, like, but in mathematics we talk about kite as a specific shape where AB equals AD and BC equals CD, right? The adjacent sides, the two pairs of adjacent sides are equal. So such figures are called as kite in mathematics, right? So in mathematics, kites are not just something which can fly in the sky when you tie a thread to it. It is a particular shape which has the adjacent sides as equal. The two pairs of adjacent sides are equal. Here you can see AB equals AD and CB equals CD. So we have learnt about trapezium, parallelogram, rectangle, square, rhombus and kite. So let's take some notes about what we have learnt. So let's look at some special criteria for these figures, some special characteristics of these figures. A square, a rectangle and rhombus are all parallelograms, right? Because all these are special cases of parallelogram where opposite sides are parallel to each other. Also, a square is a rectangle and also a rhombus, right? Why is square a rectangle? Because all the angles are 90 degrees and the opposite sides are equal, right? And in a square you can say opposite sides are equal because all the sides are equal itself. And why is square a rhombus? Because all the sides are equal and opposite sides are parallel to each other. Okay, and a parallelogram, you can call it as a trapezium also, because you can say one pair of sides are parallel. You look it in either way, from the the sides at top and bottom, or the sides on the right and left, right? You can talk about any one pair of sides and tell that parallelogram is a trapezium, right? Or you can say it in this way: all parallelograms are trapezium, but trapeziums are not parallelogram. So you can see a kite is not a parallelogram, right? A kite has only one pair of adjacent sides as equal, right? The two pairs of adjacent sides were equal in a kite, and it was not necessary for them to be parallel, right? It was not necessary for a kite, for the sides of the kite to be parallel to each other. A trapezium is not a parallelogram, as I had told you, as only one pair of opposite sides is parallel in a trapezium, and we require both sides to be parallel in a parallelogram. In parallelogram, both the pairs of opposite sides has to be parallel to each other, but in a trapezium we have only one pair of parallel sides. And a rectangle or a rhombus is not a square, right? It is just opposite to the first statement. A rectangle or a rhombus is not a square. And why is it so? To become a square, you have to have all sides equal, all the angles to be 90 degrees, right? And the opposite sides should be parallel to each other. Rectangle has some of the characteristics of square, of the opposite sides being parallel and equal and all the angles of 90 degrees, but all the sides are not equal in a rectangle, and in a rhombus all the angles are not 90 degrees. So let's talk more about the figure parallelogram. So let us talk about the first theorem in this case. It states a diagonal of a parallelogram divides it into two congruent triangles. So in the first part itself, why are we talking about the diagonals of a parallelogram, where we can talk about diagonals of a square, of a rhombus, of a rectangle? Why are we talking about a parallelogram? This is because if something is true for a parallelogram, it will obviously hold for other figures also, because square, rhombus and rectangle are all special cases of a parallelogram, right? So we take a basic figure parallelogram and we are finding out different theorems based on it. So here let us see how we can show that the theorem actually holds. Let us show that the diagonal of a parallelogram actually divides it into two congruent triangles. Let us see how. So let us consider two triangles, triangle ABD and triangle CBD, right? We are considering these triangles and this triangle, right? So now we will find out whether the two triangles are equal or not by using different rules of congruency. So let us see what rule can we find out. You can see angle ABD, which is this angle ABD is equal to angle CDB, which is this angle, right? Angle ABD is equal to CBD, and what are they actually? They are alternate angles, right? You can see AB is parallel to CD and BD is acting as the transversal. So angle ABD and angle CDB are alternate angles. Also, the side BD of the two triangles are equal because they are common to each other. Angle ADB and angle CDB, what are they? Angle ADB and angle CBD, this one. And what are they? They are once again alternate angles, where AD is parallel to BC and DB is the transversal, right? So these two are alternate angles also. So you can see we have got an angle, a side and one more angle to prove that the two triangles are actually congruent to each other. So according to the equalities we have got, we find out that triangle ABD is congruent to triangle CDB by ASA rule, or these two triangles can be overlapped onto each other, and if they can be divided into equal triangles, both of their areas must be same, right? This area must be equal to this area, right? The areas for both the triangles must be equal. So you can see we have proved that the diagonal divides a parallelogram into two congruent triangles, and also we have found out that these two triangles have equal areas, right? And this is just a kind of CPCT rule, right? We are getting directly from the congruency rule. So let's talk about the next theorem. In a parallelogram, opposite sides are equal. In a parallelogram, opposite sides are equal, and how can we show it? We follow the same procedure to find out triangle ABD is congruent to triangle CDB, right? In a similar fashion we can show by using alternate angles and common sides by the same ASA rule. And so by directly from CPCT or corresponding parts of congruent triangles, we can get AB equals CD, right? AB equals CD, and also we get AD equals BC, right? We get these two equalities from our congruency rule. We get these two equalities from our congruency rule. So you can see here we have got the opposite sides of a parallelogram as equal, right? AB is equal to CD and AD is equal to BC. So in a parallelogram you can say the opposite sides are parallel to each other and also equal to each other. So let's talk about the next theorem. If each pair of opposite sides of a quadrilateral is equal, then it is a parallelogram, and you can see it is just the converse statement of what we have done earlier. We have shown that a parallelogram has the opposite sides equal, and now we are showing that if a quadrilateral has opposite sides equal, then it must be a parallelogram. So let us see how to show it. And again we use similar procedures, but here we use some different criteria. We consider the same two triangles, triangle ABD and triangle CBD. Now we are given the sides are equal, right? Opposite sides are equal. So AB equals CD, which is given, and also AD equals BC, which is also given, and obviously BD is a common side. Right? BD is a common side. So once again we get the two triangles are congruent to each other by a different rule, SSS, or side rule, right? And from this we can get, thus by CPCT we get that the alternate angles or angle ABD, which is this angle, and this angle, angle CDB, are equal. And what are these? These are nothing but alternate angles to the transversal BD, right? These are the alternate angles, and if a transversal is having alternate angles as equal, the sides which are there, which is forming the angle, which are forming the angles with the transversal, are parallel to each other, right? if a transversal has two alternate angles equal, so the sides forming the angle with the transversal must be parallel to each other, right? So we have got AB parallel to CD, and by similar way we can talk about angle ADB, which is this angle, and angle CBD, which is this angle. So these two angles are also equal, and similarly we can say that BC must be parallel to AD, right? So we have proved that it is a parallelogram. So let us come to a new theorem.
You are currently the only person in this conference.
In a parallelogram, opposite angles are equal. And how do we prove this? Look, we have proved that opposite sides of a parallelogram are equal. We have proved that the diagonal divides the parallelogram into two equal areas or two congruent triangles. And now we have to prove that opposite angles are also equal. And we can do it in the same way by showing that these two triangles are congruent to each other, or just by stating the theorem that the diagonal divides the parallelogram into two congruent triangles, and from there directly by CPCT we get angle ABD is equal to angle CDB, and also angle ADB, or this angle, is equal to angle CBD, which is this angle, right? So these two angles are equal to each other. So let us see how to show that the opposite angles are equal. So you can see we have taken these angles as x and y. Excuse me. We have taken angle ABD and angle CDB as x. This is x, this is x. And we have taken this angle, angle ADB, and angle CBD as y. And from here only you can see that angle D is nothing but x plus y, whereas angle B is y plus x, which are both the same, right? So let us write that down. Angle B is x plus y, right? Angle B was x plus y, this was angle x, this was angle y. So we have written the names of the angles, angle ABD plus angle CBD, which adds up to give angle ABC, which is nothing but angle B. Angle B is x plus y, and similarly we get angle D as y plus x, right? So x plus y must be equal to y plus x. So we have ultimately got angle B must be equal to angle D. And similarly we can get angle A equals angle C, right? By drawing a diagonal AC. We remove diagonal BD and draw diagonal AC, and again the two triangles will be congruent to each other. Again the two triangles along the diagonal AC will be congruent to each other, and from there we can get angle A is equal to angle C, right? And therefore we have got that opposite angles of a parallelogram are always equal. And also you can prove the converse of this statement, that if in a quadrilateral each pair of opposite angles is equal, then the quadrilateral must be a parallelogram. And you can use similar steps like that we have used in our earlier converse statement, right, where we have proved that if the opposite sides are equal, then the quadrilateral must be a parallelogram. Similarly, you can also show the converse of this theorem. So let us talk about a new theorem. The diagonals of a parallelogram bisect each other, or AC bisects BD, and also the other way around, BD bisects AC. So how can we show this? So we have divided the quadrilaterals along the diagonals AC and BD, and the intersection point is O. So let us consider the two triangles AOD and triangle BOC. Let us consider these two triangles. So you can see we have got angle OAD equals angle OCB, OAB, right? OAD, sorry, it is OAD, which is this angle, equals angle OCB, which is this angle, right? These two angles are equal. Why? Both of them are alternate angles, where AD is parallel to BC and AC is the transversal. And also we have got that AD equals BC, right, because the opposite sides of a parallelogram are equal. And also the blue angles, which are angle ODA and angle OBC, these two angles are also equal, as they are also alternate angles, where BD is the transversal and AD and BC are the parallel sides. So we have got three conditions for this triangle to be equal to each other, which are angle, side and angle rule. So we can say that these two triangles are congruent to each other, right? So you can see that we have proved that the two triangles are congruent to each other. Angle OAD is congruent to triangle OCB, right? And what rule have we used? We have used the ASA rule. Thus, by CPCT, we can say OD equals OB or OD equals OB, right? So you can see BD is bisected at O, and also OA equals OC, and therefore you can see AC is also bisected at O. Or you can say it like this: the line segment BD bisects AC and also AC bisects BD, or the diagonals of a parallelogram bisect each other, right? And hence AC and BD are bisected at O in the given figure. And also you can solve for the converse of this theorem, which is if the diagonals of a quadrilateral are bisecting each other, then the quadrilateral must be a parallelogram. And this statement can also be proved in similar fashion by considering the two triangles. So let us solve one question based on what we have learned so far. We have to show that the diagonals of a rhombus are perpendicular to each other. Now let us recall that rhombus is a special case of a parallelogram where opposite sides are parallel to each other and all the sides are equal to each other, right? All the sides are equal in a rhombus. So let us use these concepts to show that the diagonals of a rhombus not only bisect each other but also are perpendicular to each other. So before going into solving it, we should first draw one diagram which supports our answer. So let us take as a rhombus ABCD, where the diagonals AC and BD are bisected at O. Right? They intersect at O, and also as it is also a parallelogram, the diagonals must bisect at O also. So let us consider once again triangle AOD, this triangle, and triangle COB, triangle COD. Now we are considering two adjacent triangles. For showing that, for the proof of parallelogram earlier, for showing that the opposite sides were equal to each other, what we had done, or for showing that the diagonals bisect each other, we had taken two triangles which were not adjacent to each other, which were opposite to each other, right? And here what we are taking to prove that a rhombus has perpendicular diagonals, we are taking two adjacent triangles, and you will know why we are taking such things. Let us consider the two triangles AOD and COD, two adjacent triangles which are lying on the same straight line AC. So you can see AO equals CO because the diagonals get bisected, right? The diagonals bisect each other. So AO must equals CO, right? And also AD equals CD. And why is it so? Because it is a rhombus, right? And every rhombus has all its sides equal. So AD must be equal to CD. Then you can see OD is a common side, right? So OD must be equal for both of them, as it is common to both of them. And therefore, by the side rule or the SSS rule, we get triangle AOD and triangle COD are congruent to each other. And from this, we get that angle AOD, which is this angle, is equal to angle COD, which is this angle. These angles are equal from the orders given in the triangle, right? From the order in which they are congruent to each other, or A can be overlapped on C, O can be overlapped on O itself, and D can be overlapped on D itself. So by this order we have proved that that angle AOD is equal to angle COD, right? In this order only. So this is by CPCT. And now what we do, you can see that these two angles, as they are adjacent to each other and also they lie on the same straight line, both of them must add up to 180 degrees, or you can say angle AOD and angle COD are linear pairs, right? So angle AOD plus angle COD must be 180 degrees as they are lying on the same straight line, right? This angle and this angle, both of them are lying on the same straight line. But also angle COD is equal to angle AOD. From here we have got that, right? Angle AOD is equal to angle COD. So what can we say? If twice angle AOD is 180 degree, so 1 times angle AOD must be half of it, right? It should be 90 degrees. So we have got angle AOD as 90 degrees, right? If twice angle AOD is 180 degrees, so AOD must be equal to 90 degrees, and AOD is also equal to COD, right? Angle AOD is equal to angle COD. Therefore both the angles are 90 degrees, right? This angle is also 90 degrees, right? And this angle is also 90 degrees. And similarly, as angle AOB and angle AOD are lying on the same straight line, this angle must also be 90 degree, and also this angle will be 90 degrees. So you can see all these angles are 90 degrees, or you can say that diagonals are actually perpendicular to each other, right? So in this question what we have used that a rhombus has all its sides of equal length, and also the characteristics of a parallelogram which says that diagonals bisect each other. And like this we can use different theorems that we have learnt in case of parallelograms to use them in certain questions according to the question's demands. So here is one question, try yourself, which says two parallel lines L and M are intersected by a transversal P as shown. Line L and line M are intersected by a transversal which is named as P. Show that the quadrilaterals formed by the bisectors of the interior angle is a rectangle. Right? We have to show that the bisectors formed by the interior angles of the rectangle, by the interior angles of this figure, the quadrilateral formed by the angle bisectors of the interior angles of these figures form a rectangle. Or let me give you the diagram itself. Angle bisector of this angle will be approximately like this. The angle bisector of the other angle, the adjacent angle, will be looking like this, right? It is an approximate figure, and angle bisector of this bigger angle will look like this, right? And this angle bisector of the smaller angle will be like this, right? And so if we join the sides, this is an approximate figure. So if we join the sides, we need to show that the figure formed, this figure formed is a rectangle, right? We have to show that this figure formed by the bisectors of the interior angles is a rectangle. So note this question down, and we will see the solution in our next class. So in this class we have learnt about the introduction, we have learnt about basic concept based on quadrilaterals, different terms used, and also we have seen the angle sum of a quadrilateral, which is 360 degrees, right? Because a quadrilateral has two triangles joined back to back. We have seen different types of quadrilaterals like the trapezium, parallelogram, rectangle, square, rhombus, and then finally kite, right? And we have learnt a lot about the figure parallelogram, and we will continue with this topic in the next class, and we will move further to end our topics. Thank you, and see you again.